Hello everyone. Now we have to discuss the next concept, that is analysis of two-port networks. So what is this two-port network? So why we need this two-port networks is, in general, it is very easy to analyze any electrical network if it is represented with an equivalent model, right? So if we are represented with an equivalent model, obviously we are going to get the relation between the input and output variables. So by representing the electrical circuit with an equivalent model, we are able to get the information regarding the input as well as the output variables, means the relation between input and output we will get. So for this we can use two-port network analysis. Okay, so in this, before the discussion of two-port network, first we have to discuss what is this one-port network. Okay, one port means what? Port means what? This is the port, right, which gives the information or taken the information, right? So one port means what? One port, which is equals to what? One pair of terminals. That is, one pair of terminals means what? One pair, which is equals to what? Two terminals. So two terminals is nothing but one port. So this is one port. For example, the same like arrangement if we have on other side, obviously that is two port. So the example for one port is what? Resistor, inductor, capacitor. Means what? The amount of current which is entering at one end of the port and leaving from another end of the port. Okay, the same amount of current can be entering from one end, like that the same amount of current can be leaving from another end. So this is the case of one port. See, this is what? Simply it is a rectangular box. We can represent this, the equivalent circuit in this rectangular box. Okay, so at input side we have one pair of terminal, like that at output side we have another pair of terminal, but within that we have a rectangular box. In that we are having a equivalent circuit. That's it. So by choosing the equivalent circuit in such a manner that we have to get the relation between input and output. Okay, means you can write that any active or passive network having only two terminals can be represented by an one-port network. Any active or passive network having only two terminals can be represented and one port network. So the example for this one port network is nothing but simply we have what? Resistors, inductors and capacitors. So the current is entering from one end, like that the same amount of current can be leaving from another end. That is nothing but one port network. Now we have to discuss two port network. So here this is the equivalent model representation of two-port network. Here the at input side we have what? One pair of terminals. At output side we have another pair of terminals, right? Let us say 1 1 dash, this is 2 2 dash, right? Like that, 1 1 dash, 2 2 dash. Here the current is what? Let us say from this the current is I1. The same amount of current can be leaving from this terminal. That's it, one port, right? Like that, from this the current is entering, right? I2. The same amount of current can be leaving from this another side of the terminal. For example, if we have a current like this, the same amount of current can be leaving like this. If it is entering in this way, the same amount of current can be leaving in this way. That's it. Okay, this is about two-port network. Means what? We have 4 terminals. In addition with that, sorry, this is leaving. Like that, this is entering, this is leaving. This is I1, this is I2, right? Then what about voltage? The voltage across, this is nothing but V1. Like that, the voltage across output terminals is nothing but V2. The voltage across input terminals is nothing but V1. Like that, the voltage across output terminals is nothing but V2. Simply by representing the electrical circuit in equivalent model, we can able to get the relation between input variables and output variables. What are the input variables? V1, I1. Like that, output variables are what? V2, I2. Sorry, here the value of input variable is nothing but I1 only, because with respect to port 1, right? This is, here we have what? How many pair of terminals? We have 2 pair of terminals, right? That is, how many terminals? 2 pair of terminals means what? 1 pair should be equal to 2 terminals, therefore 4 terminals. That's it. This is about two-port network. That is, what is the example of two-port network? Simple, the rectangular box which contains the equivalent circuit of the circuit. Okay, the example for this, we all know that the example for this two-port network is transformer. See, this is the core of the transformer. For this we have winding, right? Like that, this is secondary, right? See, this is what? 1 1 dash, 2 2 dash, right? The voltage across this is nothing but V1. The voltage across this is nothing but V2. That is, across load we have to calculate the voltage, right? This is the supply voltage. Through this we have a current. Because of the supply voltage, obviously there is a current, right? I1. So because of this, actually the current leaves. The current direction is nothing but what? This direction. Okay, actually the current towards the load Now this is the actual representation of transformer. So transformer is what? Two-port network device. Transformer is what? Yeah, two-port network device. Simply by using this two-port network analysis, we can able to get the relation between input variables and output variables. So within this, in between this combination, we have a rectangular box which contains the equivalent circuit of electrical circuit, right? Like that, for example, if we have n number of ports, this is the example for n port network. Okay, let us say this is I1, I2. Okay, like that, I2, I2, sorry, this is I1. Like that, we have I3, I3, I4, I4. So across this we have a voltage. Let us say this is V1, right? Let us say this is V2, this is V3, this is V4. That's it. This is the example for n-port network. That's it. Now we have to discuss the configurations, network configurations of two-port network. So we all know that this is the representation of T section, right? It looks like what? T, right? It looks like T. That's why this section is called as T section. So in this we have what? This is impedance Z1, this is impedance Z3, this is impedance Z2, right? So we can call it as, these two are connected, right? This Z1 and Z3 are called as series arm impedances. Series arm impedances. The impedance which is connected across is nothing but shunt arm impedance, right? So from this, net, before that we can write one important point. So this is what here, Z1, Z3, Z2, right? From this Z1 not, for example, Z1 not equals to Z3, then this configuration is called as, unsymmetrical T section. Unsymmetrical T section. Why? Because Z1 not is equal to Z3. When it is called as symmetrical T section, here see, Z1 series arm impedances are equal, that is Z1 which is equals to Z1. In this side Z1, here in this side also we are having Z1, therefore this is what? Symmetrical T section. That's it. Because the reason is what? Both series arm impedances are equal. Here the series arm impedances are not equal, but in both the cases the shunt arm impedance is same, right? Reason is what? Both series or impedances are not equal. Here series arm impedances are equal. Both circuits are having what? Same shunt arm impedance, right? See, shunt arm impedance is nothing but what? Z2. Here it is also Z2. So whatever may be the circuit, the shunt arm impedance is same. So this is about unsymmetrical symmetrical T section. So coming to this side, this is what? See, here Z1 is equal to Z1, Z1 by 2 is equal to Z1 by 2, both are equal. Shunt arm impedance is Z2, shunt arm impedance is Z2, but here we have what? Z1 by 2, Z1 by 2. This is what? Unbalanced. This is unbalanced symmetrical, right? Z1 is equal to Z1, unbalanced symmetrical T section. Sir, why it is unbalanced symmetrical T section? Why it is unbalanced? Because in the upper arm we are having Z1, but in the lower arm we don't have any Z1, right? Like that, in this side also, in the upper arm we are having Z1, but in the lower arm we don't have any impedance. That's why this is unbalanced symmetrical T section. Okay, like that. This is what? Balanced symmetrical T section. Why it is balanced symmetrical T section? Because here upper arm we are having Z1 by 2, Z1 by 2, like that the same amount of impedance can be present in the lower arms. That's why this is balanced symmetrical T section. So this is about T section, unsymmetrical T section, symmetrical T section, like that unbalanced symmetrical T section, balanced symmetrical T section. Now this is what? Pi. It looks like what? See, pi, right? Pi section. So looks like pi. That's why this name is called as pi section. See, here the upper arm is nothing but what? Z1. Like that, the upper arm is nothing but Z1. Clear? Now this is Z2, Z3. Here also Z2, Z2. Then tell me which one is symmetrical, which one is unsymmetrical. We all know that. By inspection we can say this is what? Unsymmetrical pi section. Why it is unsymmetrical pi section? The reason is what? We can write later. This is the reason is what? Both shunt arm impedances are equal. Here, sorry, not equal. Both shunt arm impedances are not equal in this case. In this case, both shunt arm impedances are equal. That's it. This is unsymmetrical and symmetrical pi section. Coming to this is what? So upper arm is what? Z1, Z2, Z2. This is Z1 by 2, Z1 by 2, Z2, Z2. This is symmetrical, unbalanced, right? Unbalanced symmetrical pi section, right? Why it is unbalanced? Because we don't have any lower arm impedance. That's it. Okay, this is what? Balanced symmetrical, because all impedance values in shunt manner as well as in series manner are equal, right? That's it. This is balanced symmetrical pi section. Now we have to discuss this section is also called as, see, this looks like what? O section, or we can call it as O section. Like that, this is called as balanced symmetrical T section is called as, this is what looks like H, right? Sorry, yeah, looks like I. This is balanced symmetrical T section is nothing but, we can call it as H section. See, if we see in this direction, this is looks like H. If see in this direction, it looks like I. It may be H section or I section. It is up to you. Okay. This is pi section completed. Next, L section. That is nothing but L section. See, why it is called as L section? Because here the series arm impedance as well as the shunt arm impedance are connected in such a manner that looks like the letter L. That's why this section is called as L section. Okay, we can write an important point. For example, if we assume this section as T section, so there is no impedance in this, right? If we assume this section as impedance or T section, there is no impedance, right? No impedance in T section. So like that, if we assume this section as pi, obviously there is no shunt arm impedance, no series arm impedance. That's it. We can write that point. It may be observed that L section is a special section of asymmetrical, right? Because why it is asymmetrical? Because we don't have any series impedance in T section, right? It is a special section of asymmetrical T section, or we can say special section of asymmetrical pi section. So L section is nothing but what? Is a type of asymmetrical T section or asymmetrical pi section. That's it, right? Next, lattice section. Lattice means what? Where series arms and what? Cross arms or diagonal arms are connected in this manner. So if series arms as well as diagonal arms are connected in this manner, then that connection is called as lattice section. ZS means what? Next, ZD. Series impedances, sorry, diagonal impedances. So these are the series impedances and these are the diagonal impedances. So here which one is symmetrical section, which one is asymmetrical section? See, here we have series arm is nothing but ZS1, ZS2, ZD1, ZD2. So this is what? Unsymmetrical, right? This is what? Symmetrical, because we are having same value of series arm impedances like that diagonal impedances. So this is symmetrical. Symmetrical lattice network. This is asymmetrical lattice network, and we all know that lattice network is usually a balanced structure, because we have the discussion of this circuit, right? This is looks like Wheatstone bridge, right? While the calculation of equivalent circuits, we are having this circuit, right? So usually this is in balanced structure. Okay, this is nothing but bridge representation of lattice network. You can say that of lattice network. That's it. This is about lattice network. Next, bridge T section. In this, what is bridge T section? When the series arms of T section are bridged by an impedance. Right? Then the section is called as bridge T section. Okay, see, by looking at this, which one is symmetrical, which one is asymmetrical? Okay, here the series arms of T section are bridged by an impedance. This is bridge T section. So from this we can say that now we have Z1 by 2, Z1 by 2 series arm impedances like the Z2 shunt arm impedance. This is Z3. This is what? Unbalanced bridge T section. Unbalanced bridge T section like that. This is what? See, we are having same amount of impedances in the upper part as well as in the lower part. Both are equal. Therefore, this is what? Balanced bridge T section. That's it. This is bridge T section. Then next one is recurrent network. Recurrent network is nothing but what? A cascade of repeated sections. Nothing but a cascade of repeated sections. See, here we are having what? This is one lattice section. This is another lattice section. We are connecting in cascade manner. Means what? That is called as recurrent network. What is the definition here? A cascade of repeated sections. A cascade of repeated sections of all type of networks. See, for example, see, if we consider lattice network, we are connecting two lattice networks in cascaded manner. This is one of the example like that. we are connecting unbalanced ladder pi section. This is one set of ladder network pi section. This is another set of pi section. Those two are connected in cascade manner, like that unbalanced L section, right? This is nothing but a recurrent network. So this is the introduction of two-port network. What is the basic introduction of two-port network? Why we need this two-port network analysis? In order to get the relation between input and output variables. So in between those input and output variables, we have a rectangular box. In that the total electrical circuit can be represented. Okay, this is about two-port network. That is one-port network. Two-port network, we are having N-port network and T section, pi section, then L section, then lattice section, then bridge T section, followed by recurrent network. That's it.